Well, good evening, everybody, and welcome to Environmental Coffee House. As the chat fills up, we've got moi, Sandy Shellis, Jennifer Hynes, and Jim Massa tonight. And I actually am hosting, but this is really exciting because Jennifer and Jim haven't done a show together yet. And when we were talking earlier, it was a pretty exciting talk because all of the topics, the commonality is just really good here. I think this is going to be a wonderful talk. You are all having the pleasure of sitting with us. We are the Foomers. And if you want to guess what the Foomer is, you can leave that in the comments. And if you win, I'll let you know. Okay? So take it away, Jennifer. And Jim, welcome.
I am so pleased to be with both of you, Jim and Sandy, tonight. And we have an action-packed show here today. Today's our methane show, all methane all the time. And we're going to do a little bit of a small historical retrospective. We're going to start out with a Newsweek article that came out, I believe that was, We're going to first start out with Robert Hunziker article from Counterpunch, and that came out June 2019, and this is called The Dangerous Methane Mystery. So we're going to dive into that just to kind of see where we've been in the last year or so and where we are now. And then we're going to cover a Newsweek article that's called Sea Boiling with Methane Discovered. And this came out about a year ago. And then we're going to cover a new article that just came out in the Scientific American. And it says a new Arctic is emerging thanks to climate change. And this is talking about the new Arctic climate. So that's our direction today. So Jim, it's really good to be with you here today. So happy to do the show with you.
Thank you, Jennifer, and it's good to finally team up on this broadcast. And of course, thanks to Sandy. Always great to be with Sandy as well. So take it away, Jen.
And there.
Yeah. So this first article came out in Counterpunch June 2019, so just about like a year and 3 months ago, something like that. It's called The Dangerous Methane Mystery, and it's by one of our favorite authors, Robert Hunziker. And it features, Sandy, I think you've prepared a very nice graphic that has a good map of the Arctic in all of its parts. And we're going to dive into this, and it also features one of our favorite scientists, Natalia Shakova. And Jim has the pleasure of having known Natalia these past 20 years or so. So I'm just going to cover first couple of paragraphs, and we'll take off and see how we do. The East Siberian Arctic Shelf is the epicenter of methane-rich zone that could turn the world upside down. Still, the ESOS is not on the radar of mainstream science and not included in the calculations by the IPCC and generally not well understood. Kind of bad for such an important part of the world. It is one of the biggest mysteries of the world's climate puzzle and is highly controversial, which creates an enhanced level of uncertainty and casts shadows of doubt. The ESOS is the most extensive continental shelf in the world, as we've talked about many times here, inclusive of the Laptev Sea, the East Siberian Sea, the Russian portion of the Chukchi Sea, and all in equivalent to the combined land masses of Germany, France, Great Britain, Italy, and Japan. That's pretty big. So I guess they're saying if you combine all those countries, you get the ESOS, the landmass of the ESOS. So it's huge. It's absolutely huge. The region hosts massive quantities of methane in frozen subsea permafrost and extensively shallow waters, enough CH4 to transform the global warming cycle into a life-ending cycle. As absurd as it sounds, it is not inconceivable. Ongoing research to unravel the ESOS mystery is found in very few studies, almost none, except by Natalia Shakova, a leading authority. For example, it has been suggested that destabilization of shelf Arctic hydrates could lead to large-scale enhancement of aqueous CH4, methane, but this process was hypothesized to be negligible on the decadal century timescale. Consequently, the continental shelf of the Arctic Ocean has not been considered as a possible source of CH4. Baffling, shocking, I don't know what to say, to the atmosphere until very recently. So, Jim, I have a question for you. This seems like a really big deal. Would you agree that this is a really big deal, that it hasn't really been thought about, estimated, calculated, put in the models? IPCC is ignoring it. What do you have to say about this?
Well, it doesn't surprise me that the IPCC ignores it, because the IPCC tends to underplay everything. They lowball the estimates for CO2. If you look at a lot of their reports, they don't even include methane. So it doesn't surprise me. It's, I'm trying to be nice here, but it's kind of a dereliction of duty to not include it, because, you've got huge landmass that, when you look at the largest terrestrial ecosystem on the planet, it's the boreal forest, which is underlain by permafrost. What's locked away in the permafrost? Methane. And when you have Natalia and her husband Igor Semeletov, they've been doing a lot of the yeoman work on this. They're trying to get a handle on just how much methane is potentially locked away in the ground, in the permafrost, in the methane hydrates, in the clathrates, etc. And the other question is, which this article gets to later on, is at what rate will this stuff be released? Will it be a slow leak, or is it going to be, the article calls a big burp? Some of us scientists call it the big fart, but depending which end.
That's actually sort of appropriate.
So considering it comes out, well, cows kind of belched and farted too, so I guess. But, the question is then, if you get a huge methane event,
right,
you can then have a lot of this flammable gas in the atmosphere. Now, it seems inconceivable, but I have actually seen some models where they say if you get to a certain level, and I forget what it is offhand, that if there was a spark, you could ignite the methane in the atmosphere.
Really?
And guess what? And guess what happens when you do combustion? What gas does it use?
Oxygen.
Yeah. Exactly.
The oxygen levels on Earth are going down progressively every single year, and we're not helping it by burning up all the trees and all the forest fires and everything like that. I mean, everything that's making oxygen is kind of going away, whether it be plankton or trees.
Exactly. To that point, the biggest source of oxygen in the atmosphere is phytoplankton from the ocean. They provide some 55 to 80% of the oxygen, and the oceans are dying. And when you have this consistent stratification in the ocean, we are not getting the mixing of nutrients from below. Primary productivity is tanking. And if primary productivity is tanking, the byproduct of their activity, oxygen, will also decrease. So it is not a good situation, to be quite blunt about it.
Not a good situation. And last week, Sandy and I did a show about these methane craters. I'm sure you've been studying these methane craters like everybody else has. And they say, and you noted this in one of your comments, I think, well, when those methane craters blow, they oftentimes do ignite, right? Because there's a lot of methane that's being decompressed, and a lot of static electricity comes out when that top pops off, and that actually does ignite. So are you saying that when we get to a threshold of methane in the atmosphere that it can ignite? Is that what you're saying?
Some of the models that I have seen indicate that if you get a significant burp/fart of all this methane coming out like en masse at once from the hydrates in the ocean floor, the permafrost, what have you, whatever the sources are, you can create a situation where a spark could set the whole bugger off.
Well, then I think it wouldn't be could, but would. That's pretty darn scary, especially since, all these fires have been burning throughout the West here. I don't know if it's reached up into Alaska where you are, but up and down the United States West Coast, the whole bloody thing is on fire.
Oh, yeah.
And of course, that's consuming loads of oxygen. It's putting loads of carbon dioxide into the atmosphere. It's putting loads of particulates into the atmosphere. The sky here in Colorado is completely gray. I can't even see the Continental Divide, which is, it starts 10 miles from me. That's all completely covered with smoke and ash and everything. That's just like, it feels like the end of the world. What do you have to say about that?
Well, if you were to talk to climatologists, and this includes Natalia and Igor, because they've been doing the yeoman's work on this, as well as other folks, it is good to see that the methane question is being taken more seriously and being actually considered. But if you ask climatologists, especially who study methane, you ask them what's the thing that keeps them up at night, it's methane. How much is there in the ground? What rate will it be released, slow or quickly? And then what happens when you have if it releases very quickly, what happens when all that methane goes into the atmosphere? What then are the consequences? In Alaska, we did get the smoke from the Siberian fires over here. Right now, the jet stream and the airflows, we haven't gotten the smoke from the West Coast, but you bring up an important point, namely that as the fires burn, first of all, the ground is really dry. So because, warmer air is going to hold more moisture and it'll suck the moisture out of the ground. So the ground's really dry. You're combusting all this material and the products of CO2. And in the case of Siberia, as the fires were burning, the permafrost is thawing. I would not be surprised, I don't know if it was quantified, but I would not be surprised if some of those fires were methane combustions.
Mm-hmm. I think it's very likely. Up in the Yamal Peninsula, when these methane craters go off, and they say they have like 17 that are discovered known methane craters, the reindeer herders, which I think are primarily the population that lives up there, have seen them going off in the night, lighting up the sky with fire as they go off, combusting.
Yeah, that would not surprise me. It doesn't surprise me, actually.
It's very scary what's happening with fire in this world. Sandy and I did a show the other week where we were talking about the fires that persisted over the winter in the permafrost. And
I did a recent video on that very topic, the holdover Arctic fires, where the snow cover is insufficient to completely douse any of the flames, and the ground is so dry so that it will continue to smolder right through the winter and then just flare right back up.
Right.
And we see it here in Alaska.
Oh my gosh. And what is also scary is how deep that permafrost is. And as it thaws and it dries out, the water drains away, and all you're left with is combustible peat that is deep. And these fires dig in, so to speak. And that's why they're persisting year to year. And some of the video I've seen coming out of Siberia, people escaping the flames, running for their lives in their cars. I mean, it looks like a freaking inferno, hell on earth.
I think California's similar.
Yeah, it really is scary stuff here. I mean, and it needs to be taken seriously by politicians. Let's be blunt about it. But yeah, you've got, in addition to losing the ice lenses and stuff like that, then the ground slumps, and that creates a whole bunch of other issues. If you have any say structure built on top of the ground, and you're going to find, there's a hole in the road, or your house suddenly is twisted and snapped because the ground that you thought was solid underneath is suddenly undergone liquefaction. Basically turned to ooze. I mean,
Yeah.
It's just like, it's like crazy.
Or as in Norilsk, when that big diesel spill happened, and that was completely due to the permafrost, and the big tank basically kind of gave way as the permafrost melted, and all of a sudden you've got a massive spill up in the Arctic
11,000
Circle.
gallons, I think it was.
Unbelievable. And just going into the rivers, and of course that's going right into the Arctic Ocean then. I mean,
rivers, all any of the riparian zones that that the river feeds, the aquatic organisms, the vegetation. It's a disaster. To be blunt about it.
It's tragic. It's utterly tragic. And I mean, this if you made a movie out of it and you had all this stuff happening in the Arctic and then all these things happening up and down the West Coast and everything on fire and then being struck by hurricanes simultaneously, you would think if this was a Hollywood movie, I mean, it would be like, yeah, okay, that's a bit too much, but it makes a good story, right?
Like the day after, they took one smidgen of a scientific concept and they turned it into a movie. But there's no laughing matter. I mean, people want to, those have been poo-pooing climate change, folks. It's here right now. I mean, think about it. In calendar year 2020, we've had the major fires in Australia. We've had major fires in Siberia. We've had the West Coast fires. What you haven't heard about are the major fires burning in South America and in Africa. So basically, aside from Antarctica, there's been major fires on all the continents.
Absolutely, there has.
Every single one. It's chilling. But the layperson doesn't understand or doesn't know. And that's where we walk in and try to help. Try to get out there.
Yeah.
It's not easy.
I'd like to read a comment before we go on, just continuing on this Robert Hunziker, the dangerous methane bomb. Shakava, until very recently, comment explains in part why the IPCC does not include ESAS methane destabilization in its calculations. Meanwhile, Shakava's research has unearthed a monster in hiding, but thankfully mostly in repose. Well, maybe. I don't know if this I don't know if this methane
keep in mind,
thing
this is a year old, so
Yeah, things have changed a lot. For the moment, still, early stage warning signals are clearly noticeable. ESAS is rumbling, increasingly emitting more CH4, possibly in anticipation of a big burp, which could put the world's lights out, hopefully in another century or beyond. But based upon a reading of her latest report, Geosciences, don't count on it taking so long. Wow. Everybody wants to know, when is this going to happen? Do you get asked all the time, how long have we got? How many people have asked you, how long have we got, Jim?
I just had someone post a comment on one of my videos over on my channel asking me that very same thing. When will, like human civilization shit the bed or something like that? And I'm like saying, well, we can't make such predictions. We can only make projections based on the current data and current trends. So there you have it. I mean, I did a video segment some time ago where an Australian think tank puts forth the notion that human civilization will have totally collapsed by 2050. And that's a think tank.
So is that what you tell your
give us very long, does it?
Now that's just their assessment. Will they be right? Well, the folks who will be around in 2050 can tell us.
Yeah, there are probably some that are in our audience that will.
I'm sure.
Yeah, exactly. Yeah,
I'm
I won't
sure.
be,
And
but
they're going to have to adapt to whatever is getting thrown at them. Like
Yeah.
Antonio, who turned 28
Well,
last week.
God,
oh well.
God bless Antonio. We
We
love
love
him so
Antonio.
much.
Yeah.
So let's talk about this ESOS big fat leak, the big burp, which would be only less than 5% of the existing frozen methane deposit. It is possible that atmospheric CO2 would zoom up and go as high as 1,256 parts per million. That's kind of scary. I mean, right now we're at 416 some odd parts per million of CO2, and that would basically triple it. Jim, do you think that this is likely?
Well, let's put it this way. First of all, let's keep in mind that methane is measured in parts per billion, usually the concentration, and of course the CO2 is in parts per million. I think what they're looking at here is they're using CO2 equivalent amounts for the methane.
Is that right?
So when it's talking about the 1256, that would be how much methane would be equivalent to that. If it were CO2, it would be equivalent to that amount. I don't think it's saying that CO2. Well, maybe I'm trying to make sense of his because he used CO2 equivalents, and now I don't know if he's atmospheric CO2 equivalents. Okay, so he's not saying that CO2 itself is 1256. He's saying that the methane levels would be equivalent if CO2 was at 1256.
But not just the methane levels, the CO2, the nitrous, all the different greenhouse gases and the methane all together would be a CO2 equivalence of triple of where we're. Yeah. And what's our equivalence today? Are we at 600 parts per million equivalents today?
566, and that sounds about right. I haven't seen the latest hard numbers, but that sounds reasonable. The other thing to keep in mind is, we need to look at the Eocene, especially the early Eocene, because there are lessons contained therein that applies to what's happening today. And in the early Eocene, we had CO2 levels extremely high, over 900, pushing 1,000 parts per million. That's CO2 itself.
Wow. And
temperatures were about 9 degrees C hotter than today.
Yeah.
And there is talk, this paper that I saw, that their model indicates that by 2100, temperatures can increase 7 to 9 degrees C above pre-industrial revolution levels.
Oh, that just sounds brutal. And of course, that means that the storms are going to be really bad. The fires are going to be really bad. It's going to be a stormy, fiery world with oxygen on the decrease and heat on the increase and disasters on the half shell. Just take your pick.
It's going to be, or it is, Jen.
We're there now, but
they're actually calling it the hothouse
are
Earth.
Here.
Yeah, hothouse Earth.
They're actually calling it the hothouse Earth. The thing is that a lot of the problem, or the errors, I guess you could say, was that models had always assumed linear increases, and we now know that it's exponential increases. So
yes, it is.
So now it used to be that 3, 4, maybe 3 degrees, maybe 4 by 2100. Now people saying it's probably 4 to 5 or more. So now that 7 to 9 that was originally was kind of like, well, guys, that's a little way out there. Now it's like, that's actually not so far out there. That actually might be what comes to pass.
No, it probably will. She also says in Shaka's research, releases could potentially increase by 3 to 5 orders of magnitude, considering the sheer amount of CH4 methane preserved within the shallow ESOS seabed deposits and documented thawing rates of subsea permafrost reported recently. So it sounds to me like this is just such a disaster. It sounds like these are the good old days to me. That's what I see.
This goes back to the point I made earlier that what keeps climatologists up at night, methane. How much is there, and her work, and Igor's been, she's been concentrating on the sea floor. He's been looking at the permafrost, but together they're painting a very scary, concerning picture that there's just so much methane there. They're now finding out that's, I forget how many gigatons worth, but if that thing goes up, it's lights out for all aerobic organisms, to be quite blunt about it.
Yeah, and that's why we call it the methane bomb. Now, I guess it shouldn't be entirely shocking, but the methane denial propaganda is pretty fierce out there. I think you probably has seen some evidence of this. All sorts of unlikely characters get into the mix every so often, and you got to wonder about their motivations. But there is a sizable methane denial movement going on. Have you seen evidence of that?
I haven't, but I decided a long time ago that, yes, we need to stop the climate denial crap that goes on, but you can't, with people like those, they are so irrational, you can't use logic with them, so you're just wasting your time. I personally don't engage in it anymore. I used to. I just I don't need this shit.
Yeah.
It's frustrating. But I think, with what's happening with the West Coast with the fires, you've got what's the latest one that's parked itself on the Florida Peninsula? The storm there. You had Laura, then the next one.
Oh yeah, we had Sally the other day.
Sally,
now we've got another one brewing, I think, as well. Yeah. So they're all lined up.
Five of them all. Yeah, it was like five of them all lined up. So when you got this thing here, it's going to be pretty difficult for people to to say that this isn't due to climate change. Well, there's always been hurricanes. True, but climate change is making the storms more strong.
Yeah,
and a lot
willful.
More wallop to it. For Laura to go from a Cat 1 to a Cat 5 in 3 hours, that's unheard of.
Yeah. Willful ignorance.
Would you like to take one question?
Yeah. Do we have a question?
Yeah, we do, and I thought it was a good one. John Schmidt asks, Peter Wadhams feels Stephen Hawking's 250C worst case scenario is too high. What do you think?
His 250C?
Is that a methane scenario?
Yeah, to what does that refer?
What does that mean?
I don't know. I thought it was a question that you guys would understand, but evidently, John, if you give us a little more. We just didn't want you
units.
To forget.
We need units.
Okay, we didn't want the chat to we wanted them to know that we are paying attention.
Okay.
I'm giving it back to you. Where to, guys?
Stephen Hawking, okay, great astrophysicist.
His
expertise here, I should say. That's like me trying to tell, an endocrinologist what to do. It's like, no.
Anyway, God rest his soul. Stephen Hawking's is dead and gone. He had a tough life as well, Let's move on to the next thing, guys. This is an article that came out about a year ago, just a little less than a year ago in Newsweek. It's called Sea Boiling with Methane. Sea boiling with methane discovered in Siberia. No one has ever recorded anything like this before, unless you've been paying attention. Then you've seen this. So I'm sure that Natalia and Igor have seen these seas boiling with methane all the time. I'm just going to go ahead and read a little bit, and this also mentions Igor Semiletov. Scientists in Siberia have discovered an area of sea that is boiling with methane, with bubbles that okay, as you say, Jim, it's not boiling. Bubbles that can be scooped up I read your mind there. Scooped from the water with buckets, researchers on an expedition with the East Siberian Sea said the methane fountain was unlike anything they had seen before, with concentrations of gas in the region 6 to 7 times higher than the global average. The team led by Igor Samletov and Tom. Okay, you're going to have to help me out. Tomsk
Polytechnic University.
There you go. Very nice. Thank you. In Russia.
Igor Samletov, that's Natalia's husband. So
yeah. That's awesome. Traveled to an area in the Eastern Arctic known to produce methane fountains. Now, these methane fountains can be pretty darn big. Jim, I have heard that they can be up to 1 kilometer wide. Is that true?
I seem to recall a Norwegian research team working, I think it was by Franz Josef Land, videotaping some pretty, wide bubbles. Now, what happens is, to form the hydrates in the first place, they're under pressure. And so then when you reduce the pressure, you have volume expansion of the gas, plus as the gas leaves the frozen state in conjunction with the water. So it's like when if you're scuba diving and you exhale, you watch your bubbles go to the surface. As they go shallower and shallower, the bubbles get bigger and bigger.
Mm-hmm.
So that wouldn't surprise me.
Yeah. So, I mean, this is sort of review for a lot of us, but this is Newsweek. So, locked within the permafrost is organic material. When the ground thaws, this material starts to break down, and as it does, it releases methane, a greenhouse gas, far more potent than carbon dioxide, as we know. And I've heard, Jim, that when methane first emerges into the atmosphere in its virgin state, it's up to 125 times stronger molecule for molecule than carbon dioxide. So it's pretty powerful stuff.
It is. And now we're finding out, recent research, that nitrous oxide is not an insignificant amount of gas being released as well from the thawing permafrost. So there's another GHG. So we're, between the CO2, the CH4, and the N2O, and don't forget, water vapor itself is a greenhouse gas. I mean, when you burn octane, which is a type of alkane, the products are carbon dioxide and water vapor. Just look at a tailpipe that's dripping away. So it's not just CO2 that you put into the atmosphere when you run your vehicle, it's also water vapor, and water vapor is an extremely effective greenhouse gas as well. So there's really like 4 major greenhouse gases that that are being introduced into the atmosphere and really changing the balance of things.
Right, in quantity, huge amounts.
Yes, absolutely.
So the permafrost is thawing, and this is causing more methane to be released, leading to even more warming, otherwise known as a feedback loop. Also possibly a runaway feedback loop, kind of self-propelled. It's a positive feedback loop. Do you think that we're in runaway? Do you think that we are?
Positive does not mean good.
Exactly. Good thing to note.
Positive feedback loop actually means a runaway system. That's what it means, because it keeps amplifying itself. Think of like polar amplification, which I know you know about. So you have a positive feedback loop is the self-amplifying one, meaning it gets worse and worse. A negative feedback loop are corrective ones.
Yeah.
Think of oscillating around an ideal situation. That's a negative feedback loop.
Yeah, absolutely. So hypothetically speaking, Jim, this is a completely hypothetical, unrealistic question. If all the humans mysteriously were transmuted to another plane of existence, right? And they were no longer here, and our entire civilization ceased. Given the momentum that's already in the system, what would happen if we never emitted a single more greenhouse gas from human civilization, period?
Well,
Current state.
First of all, planet Earth would probably breathe a sigh of relief. But
Yeah, I think you're.
But actually, you brought up a very important concept, and that was the momentum. I've been saying for some time, and the research, the data indicates that this is the case. There is enough thermal inertia, thermal energy in the system that warming will continue. Now, for how long depends on whatever physical processes occur. But there is enough thermal inertia in the system that warming will continue, even if humans were to disappear right now and not emit another molecule. But here's the thing. Humans could disappear right now. There are thousands and thousands of capped methane, gas places, places where they drilled for methane, but it's no longer used, so they just cap it. Well, these caps are leaking. So you got methane leaking out of these no longer used drill sites. Go to Prudhoe Bay. Okay, of course, Prudhoe Bay is actively under human activity, but you've got what? You see them flaring off the methane. A lot of these refineries flare off methane, which is ridiculous.
It's just horrendous.
So to answer your question, there's enough thermal inertia that warming will continue. For how long and to what further increase, difficult to say.
Yeah. So the other thing I wanted to talk to you about, Jim, was a little bit of history, ancient history. This has happened before. There have been hundreds of pockmarks that have been discovered at the bottom of the Barents Sea, right? Do you know about these pockmarks, these methane craters?
Yeah.
These craters had formed from methane building up in them and exploding suddenly when pressures got too high. These are pretty sizable pockmarks. And the other thing about these pockmarks that I would like to mention is that they've got groove lines etched in them, which means that ice was sliding down a hill, scraping on them, and I think that happened first, and then the methane started cratering out and popping out. So this
are you saying that the ice basically helped pop the pimple?
Well, I don't know that it actually helped to pop the pimple, but I do think that you can see that this has happened, the groove marks and the methane craters. And I think actually the groove marks come first. So that's the sliding of the glaciers, like, when all those glaciers all over the place slide into the sea, they leave these big giant groove marks, and then on top of the groove marks are methane craters, which means then the sea gets even more hot and the methane comes out. So this is kind of historically how the Earth takes care of this situation, right? So this has happened before.
It's like everything else, it's a cycle. I mean, because people say, well, the Earth's been warmer in the past, and there's CO2 levels have been very high in the past, which is all true, but you have to look at what it has been for the last several million years. You have to look at the rate of change. A lot of these other processes occur over much longer time frames, versus centuries, maybe millennia versus years or decades.
That's right.
So
I mean,
I keep stressing it's the rate of change that is what it's not just the levels and what we're putting into the atmosphere, but it's the rate of change, how fast we're doing it.
And the momentum that's incurred with that very quickening, exponentiating rate of change. And I always think back, not that we were here to experience it, but as much as we know about the Permian mass extinction, that was the worst extinction ever to afflict planet Earth. 95% of all creatures on Earth died in that extinction, but it took a bit of time to set in. It was not as instantaneous. We're going into this 6th great extinction a lot faster than the Permian extinction was launched into. We could end up going a lot deeper as well, which is kind of scary.
It is.
What do you think about that?
Well, I totally agree with you. With I just saw a number. Oh, if I can remember what the number was, something like 800 species every day go extinct. Something like that. I'm not sure of the number, but it was a significant number, and we're talking about plants, mammals, birds, amphibians, inverts, what have you. But some 800 every day going extinct, and so the Permian extinction was a big event. It did nearly wipe out all life on the planet, and we're on a track to rival that, if not surpass it, but in a much shorter time frame, unfortunately.
We certainly live in interesting times, and not in a good way.
Not in a good way at all. No.
Not in a good way. If you don't mind, Jim, I'd like to turn to our last article. A new Arctic is emerging thanks to climate change. And this one came out 2 days ago. And there's an entire new Arctic in terms of climate. Temperatures are skyrocketing, sea ice is dwindling, and many experts believe that it is transforming into something unrecognizable. Have you had the opportunity yourself, Jim, to travel into the Arctic regions, being in Alaska, as you are?
The Chukchi Sea was my office.
That would be a yes.
Yeah.
That would be a yes.
It's interesting because I'm actually preparing an article based on something Dr. Paul Beckwith has done, where he calls it BOE. BOE, you may or may not know.
Blue Ocean Event. Oh, yeah.
Blue Ocean Event. Yeah, I knew you would know that, but he's basically talking that when the Arctic Ocean could become ice free, and then they talked about BOE +2, +4, +10, meaning that BOE would be okay. We have like a month or two of ice free. Then BO2 +2 is we have 4 months, +4 we have 7 months, and then +10 is it's ice free year round.
Mm-hmm. That's right. Well, that's really the only thing that's keeping this whole system semi-intact, although it's pulling back. The Arctic sea ice is pulled back so far, and it's getting so mushy. And of course, that's the only thing that's kind of keeping this methane under wraps. But of course, we can see it's not being kept under wraps anymore. What is your opinion as to when are we going to have this first Blue Ocean event up in the Arctic, meaning technically less than 1 million square kilometers of mushy sea ice?
They're saying 2022 now.
2022. Okay, that's bad.
2024 at the latest is what they're saying. And they're saying that it could very well be that by 2035 we might be in that BOE +10 situation. Which is because don't forget you have the sea ice in the Arctic, you have Antarctica, so you got these two massive things of ice having high albedo, right? Reflects a lot of the heat energy back into space. Well, now we're losing the albedo from the Arctic side of things, so now instead of that sun energy being reflected back into space, the open water absorbs it. And that just heats up everything. Then you have latent heat energy, which is why the air stays warmer. Also, this is why the sea ice is freezing later in the year, because the water is still above freezing. And don't forget, to freeze seawater, you have to go below 0 degrees C because of freezing point depression due to the salinity content. So you actually have to freeze the water at a lower temperature, like -2, -3. Or so C. So you have that situation, and this is just going to cascade. It's going to affect jet streams. It's going to affect productivity in the Arctic Ocean, we're setting up for something really bad.
And really quick from the
Very quick, yes.
Yeah, quicker than expected. It's very hard to think about these things as possible realities when everything is still sort of intact, although we're seeing apocalyptic events wherever we look from a climate perspective. But, if you're really unaware, you can fool yourself into thinking that it will always be this way. But clearly, it won't always be this way. And
don't forget, when you have no sea ice, you don't have the ice protecting the coastlines. So now you have storms, and storms are going to just batter the crap out of the coastline. Then you have the erosion from wave action, the thawing permafrost. You have whole chunks of coastline just boom dropping right into the ocean. There are villages, for example, in Alaska that have to totally relocate, and we're talking quite a few miles further inland, because literally the ground is dropping off from underneath them.
Yeah, it's absolutely shocking. I have seen those different Inuit communities. Is one of the islands called Kavalina or something like that?
There's one of those Kaktovik, which is off the coast of what's called the ANWR, the Area 1002 spot.
And what most people don't realize, when you try and relocate and rebuild a whole town or village, it's pretty damn expensive, more expensive than you would think, because you just are thinking, oh, well, we'll just buy them houses. No, you're reconstructing a village with all of its infrastructure, all of its community things and schools and God knows what else they may have. They may only be a couple of hundred people, like 400 people or something like that. But, if their community is being submerged and swamped by these big storms, they have to build somewhere else. And it is a pretty expensive proposition to build a new village.
It is. And not only that, your isolated village where you don't have a road system, so you can't travel until wintertime because you can't travel on the tundra. The vegetation is extremely delicate and fragile, so you have to wait until things literally freeze over before you can even think of moving. And then there's the cost of diesel, and it's, as you said, it's extremely expensive. Then you have generators to supply the power, and it's not a very simple thing to do.
No, it's not. We're just a bundle of good news today.
No, this is the stark reality. This is what we're facing.
It is.
Another place I used to go to a bit was Inuvik, which is in the Yukon Territory, and over to what's called Tuktoyaktuk, which we just call Tuk for short. But it's literally a village right on the edge of the Mackenzie River Delta, and there's a barrier island that's around this village. That barrier island is falling into the Arctic Ocean. They are now completely exposed and vulnerable to storms there. And when you look at photos of this village, we're talking a mean elevation above sea level of like 3 feet. It's right there on the water, and they're going to get swamped.
Absolutely, they are. It's so sad. It's a really, really tragic time to be alive. And sea level, we've been talking about global warming. We've been talking about methane. We've been talking about all these things, and kind of just haven't even mentioned sea level rise, which notably it is a lot slower than this methane release is going to be, but it's irrevocable, it's unstoppable, and it's happening right now, and it's exponentiating. What do you see from an exponential point of view, how sea level rise is going to progress, and what kind of sea level rise do you think that we're going to be seeing, say, by 2100 or something like that, if there's any of us to see it?
Well, if we were to take into account all of Greenland's ice, if we were to take into account the main glaciers in Antarctica, Thwaites, Pine Island, Ross, the Brunt ice shelf, those guys there. And Thwaites, by the way, is scientists are extremely concerned about that. It appears to be an imminent collapse, the Thwaites. And Thwaites goes, Pine Island is not too far behind it, to be honest. So they are monitoring that as best as they can because it's a hard place to reach. This is the logistics of getting stuff there. I've seen estimates, ranging from, let's take Greenland alone. If all that goes, I'm hearing 3 meters, something like that. You start throwing in all these other glaciers, we're talking 25 to even 75 meters of sea level.
It's going to melt down really fast. It's really shocking how quickly it's melting down.
And don't forget, you also have the thermal expansion of water itself because the water is heating up as well.
Yes, that's right.
So it's not just simply the input of the melt water, it's now the thermal expansion as well that will bring up sea level. Now, that thermal expansion has been measured on the order of like 1, 2, maybe 3 millimeters, something like that. But it's still, when you consider these, the planet should be called Oceanus. It's an ocean planet.
It is an ocean.
And you consider the surface area, that's a big area. That's a significant amount of expansion.
It's amazing. And the level of denial to contend with these future realities is causing people to continue to build condos right on the ocean, up and down the coast of Florida, pretty much up and down the coast of the United States. And the eastern United States is subsiding anyway. So it's kind of a bit of a double whammy there, along the Virginia Beach area and things like that. Well, What other bit of infrastructure might there be just at the end of the Chesapeake and up the Potomac? Right?
Well, here's the other thing. You have seawater.
We're talking Washington, D.C.
Oh, yeah. You have seawater, for example, getting into Miami. We know what's going to happen. You're going to have seawater getting into the groundwater table. You're going to start getting brine water into the drinking system. Well, you can't drink brine.
No,
so you're going to have brine infiltration. We're already seeing brine infiltration in the Oglala Reservoir because they suck the damn thing dry. But, you're already seeing that there. We're seeing it in Miami. So logically, we're going to see that up and down the East Coast, that you're just going to have the saltwater intrusion. And that's going to render drinking water unpotable. Was it non-potable?
Oh, my goodness. It is a shocking and tragic time to be alive, but it's also kind of fascinating. I really prefer, and some people don't like to look at it clearly, that's why they're not here with us, but I really prefer to watch the approach of the oncoming train. I mean, we're here, might as well take a look at it and see it. It takes a little bit of courage, right, to look at this, but at the same time, once you know it, you can't unknow it. Do you find this kind of keeping you up at night? Or not?
Does it keep me up at night? Maybe because I'm not 28 years old, I'd say no, but but it doesn't mean that I'm not concerned. Of course, I'm concerned, and that's an interesting metaphor to use because you talk about the train coming. Trains have a lot of momentum. It's hard to stop the train.
Can't stop a train.
And basically, we've got this momentum going, and get out of the way.
I kind of always equate it with like that Thelma and Louise feeling of just driving off. And it's Jennifer. Somebody should put you and me in the convertible in the front, just driving off.
We totally should do it.
Yeah.
I mean,
if I can do something graphic. But we'll have methane in it. We'll have methane in it. I'll find some way to put methane in it.
Oh,
so,
Sandy.
what I wanted to tell you guys, even though I said I'm staying behind, but Jim does have those graphs if you wanted to look at them and discuss them. We're going on 55 minutes, but we have 104 people with us. And would you like to talk about any of the graphs?
Sure, we could. Jim, do you want to start to go through. Sandy, are you able to display those graphs on the
I
screen?
am able to do that. I'm going to do that. The first, let me get rid of the articles.
Jennifer, did you want to say anything further about this Scientific American article, or just go on?
Oh, I think we're ready to segue on. We've got limited time, so we'll just we always put the articles in the show notes, so people probably read them afterwards on their own. We kind of just sort of get their whet their taste, right? So this first one that you sent over, the global surface temperature relative to 1880 to 1920 mean, is this sea surface temperature that we're looking at?
Let me get the right one too.
Or is this just surface temperature in general, land, sea, everything?
Okay, I'm going to, it's not appearing on my screen here, so I'm just going to go into my email and pull it up from there.
Yeah, that's what I've done as well.
So let's see.
Well, while you're pulling that up, I will let people know what we're about to look at. So there's a few graphs that Jim sent over via email, and they all are good examples of the exponential function. Everything is going up with the curve, meaning that it's going to be a little bit steeper in the future, meaning it's going to be more extreme in the future. And it's happening in every single measurement. This first one was global surface temperature relative to 1880. And this is I think this is just the surface temperature of Earth, Jim, if I'm not mistaken. Is that correct, or is this ocean?
It's the one from 1880 to 1920 mean relative to that.
Yes, is that ocean surface temperature?
That's global surface temperature. That's the entire
global
planet.
Surface temperature.
So that's
the entire planet?
land and sea.
Yeah.
So the entire planet surface. So basically, what they're doing is they're using the 40-year period from 1880 to 1920 as a baseline, and any deviations from that average baseline. So when you look at the vertical graph, it's the zero means no departure from that 40-year average. If it's negative, it's cooler than that. If it's positive, it's warmer than that. So it would be like, say, 0.4 degrees C warmer than that average, whatever that may be. And when you look at that, especially starting in about 1970 or so, you can pretty much see it's a shot up. It's just shooting right straight up there.
And that's what I always say, just look at the trends, look at where you're going. Don't get too concerned about cherry picking some short amount of data, as they did cherry pick it. Remember, they used to say, there's no global warming since 1998. Well, that was a super El Nino. It got pumped up, and then it just kind of leveled off for 12 years or so. And then we're off back to the races again. So, people are brilliant with cherry picking data and trying to make their point. Better to look at the whole trend and understand exactly where you're going.
But see, the thing is, though, climatologists do account for whatever natural variability signals that may be present. For example, if you look at that chart there, they indicate some of the super El Ninos there. So they do indicate for that, and they do remove any signal, especially when they're computing, like in this one here, 132-month running mean. That's 11 years. Okay, so that's, so the smoothing out for that. And then the green line, you've got the best linear fit from 1970 to 2020. That's 50 years. And if you look at that, the slope is obviously positive. And so then people say, well, what about you got the 12-month running mean, and it looks kind of cyclical. Well, this thing's called seasons, that, and that's why you're going to see the ups and downs.
That's right. That's right.
So people will look at that and say it's just noise, and no, you got to. I call the jagged line weather and the slope of the line climate. If you,
exactly.
Put it in
exactly.
those kind of terms.
Exactly. So the trends are basically climate.
The
if you look
at trend.
trends over time. And if we look at the next graph, the global monthly mean CH4 methane, this is a methane concentration parts per billion. You can see that after our little super El Nino and things leveled out, that's the part that climate deniers like to pick that one little area and say, oh, see, no more global warming. But it's off to the races
but
again.
ENSO doesn't affect methane. It's like, so it's it's again they just as you're saying, the cherry picking. But what's interesting is, and I've actually seen some graphs on this, and I'm featuring some of these graphics in an upcoming video I'm putting together. But there's actually 3 sections to this overall methane. And what's interesting is if you look in the section that's in the middle there, it kind of almost looks like the slope is a little shallower.
Do I have the right graph up?
Yeah, you do.
The recent
I'm talking
trends?
about methane trend. I'm talking about some other graphs that I've seen that zero in on specific intervals of time, like 10, 20 years or so. There's a stretch in there starting from like the mid 90s into about the mid 00s where the methane levels decrease a little bit. And the hypothesis that I have, and I'm wondering, Jennifer, if you have seen any papers addressing it, because I haven't. We had the mad cow situation that happened in the 1990s where they slaughtered 4 to 6 million cattle. So I'm wondering if the little drop in signal, this is my hypothesis at least, if the little drop in signal of the methane level was because you had 4 to 6 million less cattle farting away.
Well, that could have something to do with it. It's possible. And I think it also kind of coincides with that super El Nino and the leveling out of the temperatures for about 12 years or so. That would also coincide with it. So maybe the slaughtering of the cattle, several 100 million cattle, and then the leveling of the temperatures, that could create kind of a shallower curve there. And then, but it just picks right up. I mean, right when you get to about 2007, which coincidentally was the first really big dip in Arctic sea ice extent. 2007 was when it really went down sharply for the first time. And I don't know. You just put all this together. It's interesting.
There are several factors that can explain the increase since 07. One, I think, is the building up the cattle number, so back to the pre-mad cow. But you also have, as you just said, the methane being released from the permafrost, clathrates, hydrates, and so on. You have fracking, which is a methane intensive putting into the ground. You have rice paddies.
True.
So those are all major sources of additional methane.
Oh, that's true. That's interesting. We're getting kind of long, so let's kind of cover the next few ones. So this next one, Sandy, this is the global ocean heat content. And about 93% of the heat produced by civilization is absorbed into the ocean. So consequently, the ocean heat content is going up higher and higher and higher. You can see kind of the similar sort of pattern. Jim, would you like to talk to this graph a little bit? Kind of what you feel?
This is something I've been looking for, some quantifiable, especially over the long term, data on the heat issue into the ocean, because I've been saying for some time that the oceans have so far to this point been saving our bacon because they've been absorbing so much of the CO2 and so much of the heat. And as you can see from this graph, the amount of heat that the ocean is absorbing keeps increasing. But here's the interesting thing. It's from 0 to 2,000 meters. Now, you always have a seasonal pycnocline in the ocean, upper ocean layers, a couple of 100 meters or so. But when you go down in the ocean depth, you have what's called a permanent pycnocline, which is a sharp change in density that can be at 1,000, 1,500 meters or so, usually around there, sometimes down to 2,000. So we're talking about basically from the permanent pycnocline to the surface. And so now the question is, how does heat get all the way down to that level. That's the vertical currents, the vertical mixing, the thermohaline currents that take place in AMOC and the Jin Sea when you have this water sinking to form to start the conveyor belt. That is bringing heat and CO2 out of surface waters down to depth. Well, as you know, gas solubility decreases with an increase in temperature. So at some point, the water is no longer going to be able to keep absorbing the CO2. It's going to stop absorbing CO2, and as it keeps warming, at some point it's going to start outgassing the CO2 in the water back into the atmosphere. So there's another whammy waiting to hit us. And researchers at Halifax University, Dalhousie University in Halifax, Dartmouth, Nova Scotia, they have been measuring the slowdown in the deep water formation. So if you have the deep water formation slowing down, you're not going to sequester all this material. You're not going to sequester the heat and the CO2, so you're going to further saturate this upper surface layers and increasing the outgassing back into the atmosphere. So this is I consider this an extremely important graphic.
Yes, absolutely. And while we're on the topic of hot ocean water, I'd like to just draw attention to the hot blob of water in the Arctic Ocean that is at depth. And this is the Atlantic hotter, salty water that is actually hotter than the surface water. And the surface water is quite fresh, quite cool, because it's basically ice melt. And this big giant blob of hot water is in the Arctic Ocean at depth, and it is slowly starting to mix more and more. It's been kind of held off by this barrier of the fresh light water, but that's not going to last forever. Can you talk about this mixing in the Arctic Ocean and why it's so dangerous?
One of the most difficult concepts for oceanography students to get a handle on are looking at what we call TS curves. There's the temperature salinity curves, because ocean water density is determined not just only by temperature, but by salt content. So yes, the Atlantic water is warmer, but it's saltier. So in that particular combination, it happens to be more dense than the colder but far less saline upper waters. But yes, that Atlantic water is working its way to the surface. So when you get these regimes, and this is an exact question, is that which is more dense, warm salty water or cold not salty water? Well, it depends on the mixing regime and the actual processes happening at that location. So we're seeing a lot of dynamic stuff here, and the Atlantic water does move in. It's called the North Atlantic Intermediate water. The Barents Sea, for example, is undergoing what we're calling Atlantification, because the Barents Sea is now starting to assume properties that are more typical of North Atlantic oceanic water than Arctic oceanic water. So we're seeing this intrusion and this mixing, which is going to further change the physical characteristics of everything.
Mm-hmm. Absolutely, it is a very scary thing. Let's progress on to the next graph. It's called Recent Global Monthly Mean CH4 methane. So this is basically taking a recent look at the methane cyclical increases, annual increases from 2016 to present. So it's the last 4 years, and it seems pretty steady. It's kind of almost like a heartbeat, except it's going up in a polynomial trend line.
Yeah, take the EKG and tilt it, right?
Yeah, exactly. What do you see when you look at this?
Obviously the red dots and dashed lines is the seasonal, going through the seasonal cycles there. What we see is a very clear increasing trend. And that's most likely attributed to the factors we mentioned earlier. But the trend is unmistakable. It's increasing, and probably will continue to increase.
Mhm. And our last graph is atmospheric CO2 concentration. And this, of course, goes from pretty much when they started measuring CO2 in Hawaii, I think it was Mauna Loa or something, from 1960 until the present time. So that's 60 years of CO2 collection on a daily basis, and you put it all together and you get this graph that just marches on and on and on, and it doesn't look like it's ever going to stop. It looks like it's pretty well dedicated to this upward trend.
It is. And if you take this particular graph, the one of the methane that we did earlier, past more than the 4 years, and then look at the temperature, you can see how it's all correlated. That the temperature is responding to the increased levels of methane and CO2, CH4 increasing, so are the temperature. It's right there, showing a direct response to the forcing from the CH4 and the CO2.
Wow.
The data is unmistakable.
It is unmistakable, and it's a real big WASF. We are so fucked. Anybody who looks at all this data and puts it together, I mean, you've got to develop some sort of gallows humor to deal with it. How do you deal with knowing this information, holding this information, explaining this information? How do you deal with this?
I kind of detach myself from it. I put on my little scientist hat. Might squeeze my head a little bit, but I put on my scientist hat and I just look at the data and it says, okay, what's the data telling me? I look at the papers, the peer-reviewed stuff, all the detail boring stuff, but that, which is why when I do my channels, I don't pull up the actual research paper, because it'd be like, like that. But I look at the data, look at the analyses, analyze it, and basically just, I kind of take it upon what I try to do, what you try to do, what Sandy's doing. It's like, here's the information. Here's the best science we have. Mm-hmm. As I stress in my videos, it's like, this is what us scientists do. We collect the information, we collect the data, we do the analysis, we do the best analysis we can, we do the statistics, the calculus, the modeling, what have you. We present our findings. And say, oh, you've got ulterior motives. That's bullshit. Our only motive is to present the best information that we have, that we can do. And it's up to the politicians. We can make our recommendations, but it's up to the politicians to get off their asses and implement our recommendations. And thus far, they're not. We now have the Arctic opening up. Already there's a rush between Russia, China, the U.S., all these, polar, circumpolar countries. Let's go extract the resources. You just want to do a facepalm.
I know you really do. But, it's kind of like the scientist's duty to teach and to explain and to make understandable to lay people and get them excited and get them passionate about exploring this also. And as we have found with Environmental Coffee House, with your show, with many other shows that are out there right now, there are a lot of people out there that really like to look at this stuff and really like to dive into it. There are closet nerds all over the place. So, we're all kind of like the choir preaching to the choir. We're all kind of, it's we've got our own little bubble. Do you see this getting out of our little bubble and actually penetrating into other places?
This is why I do what I do. I want to present the information, but I also want to explain it in such a way so that, as you say, the layperson can understand it, which often explains why I put together a whole pile of PowerPoint presentations, because I'm trying to put it all together. Or take a simple concept like, what is ENSO? Okay, here's the video. Okay, what is the Arctic oscillation? Here's the video on it. Here are the graphs. This is what explains it. That kind of stuff. I just did something on ice algae because I mentioned that in another video. Okay, I'll do something on ice algae. So I'm always trying to explain to folks, what's going on. I try to explain the concept so that they can then, if they will go to a website and they look at a graph, they say, oh, I understand what I'm looking at because this guy over here explained it. That's what I'm trying to do. I'm trying to disseminate this information, and I'm hoping that it reaches more and more people because, like it or not, despite ignorance being bliss, knowledge is power, and that's what we're trying to do. We're trying to get the knowledge out there.
Knowledge is power.
Yeah, absolutely. That's awesome. Well, I think we're sort of at the end of our show, Sandy. It's about 17 minutes after the hour. It has been a real pleasure, Jim. It has been
captivating me.
It has been a pleasure.
Yeah.
Likewise, this has been a load of fun.
Yeah.
A lot of fun with a lot of difficult information. And how do we do it? We all do it in a way that we do it, but learning is my way and presenting. So I want to thank everybody for coming. Jennifer, any last words?
Oh no, I've been talking my head off. But I mean, I guess the only thing I would say is keep excited and looking at the data, because this is probably like one of the most historic, epic times that humanity has ever lived through, bar none. So yeah, it's terrible. Yeah, we are so fucked. I do believe that. But at the same time, keep looking at it because it's pretty interesting to see what's happening here.
Yeah,
it is. I mean, and I kind of consider it as one of my roles, one of my functions is to take the data, take the information, take the research as published in peer-reviewed journals. I tend to concentrate on those. About 97% of my presentations are based on that, but I want to present the information. Well, here's what's going on, here's what they're finding, and distill the information, get it out there. And don't forget there's other things going on, like the yield of crops decreasing, the nutritional value of crops decreasing. I mean, there's just so many things going on that sometimes it can be overwhelming. I talk a lot about the Arctic because what happens in the Arctic doesn't stay in the Arctic.
True.
I also I spent many years there. I'm still here, right, in the Arctic. So as I said earlier, that was my office. So
hey, and we had a great connection tonight too.
That's great.
It didn't seem to be a blip. You're up there in the Arctic, and Jen's in Colorado, and I'm here in Western New York, and there you go.
Triangulate.
There you go.
All right, everybody. Us boomers
all right.
We are peacing out, man. I'm gonna play
this
the
is
end.
great, Jennifer. That was really cool.
It was a lot of fun, Jim. I really would like to do this again.
Definitely,
we will.
for sure.
You will.
And Sandy, as always, you're great.
I'm just silly. I try to make a good time, even though it's tough stuff. All right. Farewell.
All right. Peace
All
out.
right, guys.